A set is a well-defined collection of objects, which could be numbers, alphabets, names of persons, names of places. The condition is that it is well-defined. From the example we have here, see that the set is represented with the uppercase letter, while the element of the set is represented with the lowercase letter. That is in the case of the alphabet. So this is our set A, and these are the elements of the set, that are the members. This is our set B, and these are the elements of set B, which are the members of this family. So from this we can say that A is an element of set A. This reads A is an element or a member. This symbol denotes an element or member of this set. Like I said, this is the set, this is the member of it. Then we say B is an element of set A, because we define our set A as a set of English alphabet. The second one, we have that B is not an element of B, where A is an element of B, because this B is not part of this set based on how we define it. So it's just basically the way the set is defined. For this one, we see that there is a set of numbers. 1 is an element of D, 2 is an element of set D, but 1 is not an element of E. Why? Because we define our set E as this, which clearly is the set of even numbers. So the set is just basically how it is defined. You can define a set in countless ways. And now if you observe very well, this our set, some of them are finite while some are infinite. Yes, a set can be finite and another set can be infinite. What do we mean by a finite set? A set is finite if the number of elements in the set is known. Like from this our first case, now our first set here, set A, we'll see that if we can number these elements of this set, that is the members of this set. They are A, B, C. This ellipsis means it continues up to Z, which we know it is 26 in number. This is our set B, the set of vowel A, E, I, O, U. It is 5 in number. So these two sets, they are both finite. Now in the case of set B and set E, if you observe very well, you see that it runs to infinity. That means we cannot number them. It continues to infinity, but in this case we say it is countably infinite. Although we can count, but we can't exhaust them, so they are infinite. The same thing applies here. So these two sets are infinite, while these two sets are finite. Now if you look at the other side, you see that we represented this set in a different way. What we have here is exactly the same thing as what we have here, just that we use a different notation for this one. This tells us that set can be described mathematically in two ways. The first method which we use here is called the listing method, while this method is called the set builder method. Under this listing method, we list out all the possible elements of the set, while in this case we describe the set. In this first case, we describe the set as the set of English alphabet. So to bring out all the English alphabet, it makes set A. In this second set B, we say that it's a set of vowel. So when we collect the set of vowel, it makes our set B. This one is a set of natural numbers. Those are our counting numbers. Then our set D, we call it the set of even numbers. Either of these two are correct. It just depends on the most convenient in a case study. So now you pause this video for 5 seconds, and in the comment below, you give one example of an infinite set using this set builder notation. Put it in the comment below. Let's see. Moving further, we delve into the concept of subsets and supersets. I will say that consider two given sets A and B. If A contains every element in B, then B is called a subset of A, while A is a superset of B. Now, from our previous example, we define set A as a set of alphabets up to Z. And we define set B as a set of vowels. So we can see clearly that every element in B is contained in A. So we say that B is a subset of A, while A is a superset of B, and it's represented this way: B is a subset of A, while A is a superset of B. Now this can be seen as that B is less than or equal to A or something like that. You know, one of the best way to learn mathematics is to relate it to something you already know before. So in this case, we say B is a subset of A. Now this can also be written as B is a proper subset of A. Now The difference between these two symbols is that in this case now, B is completely contained in A. That means there is at least one element in A that is not in B. So it is totally contained in A. So we say that it is a proper subset of A. And also you can say that A is a proper superset of B. Assuming we have another set, let's call it set C, for example, and we define it as I, O, E, A, U. If you look at this set, you see that it is similar to set B, just that the arrangement of the elements are different. But from the definition of subset, every element in C is in B, and every element in B is also in C. So we can say that B is a subset of C. Now it is not a proper subset because you cannot find any element in C that is not in B. That means they are similar, but we can say B is a subset of C and C is also a subset of B. Now this is pointing us towards an important property in set theory, which we call the equality of sets. Moving on, the theorem of equality of sets states that two sets B and C are equal if B is a subset of C and C is also a subset of B. Now if you recall the previous example, we gave that set B is this. We have this our set B, and our set C we have as and from the definition of a subset, you see that B is a subset of set C and C is also a subset of set B. Now, the definition of equality of set, it is clear that B is equal to C. This shows us that since these two sets are equal, that means the order of arrangement in set does not matter, because every element in B is also in C and every element in C is also in B. That means they are equal. It tells us that the order of arrangement, whatever element comes first or last, does not matter in set. The only thing that matters is just the presence of that element in the set. So this is what the equality of set reveals to us. So the order of arrangement in a set does not matter, and this theorem is used to solve a lot of problems in set theory, which we will see in the subsequent videos. If two sets are not equal, obviously they are equal. If you have another set F now, for example, defined as O, I, U. Although this is a set of vowels, but it does not contain all the vowels. So we say that B is not equal to F. Rather, F is a proper subset of B, or you can say it is a subset of B, whichever one is correct. So if two sets are not equal, they are said to be unequal, and it's represented this way. That means B is not equal to F, but B is equal to C, because they have the same element. Let's consider this exercise here. Now in the comment below, indicate which of these two sets are equal. Set A and set B, set K and set L, set H and set G. In the comment below, just indicate which of the sets are equal, and we are going to see the correct answer. So thank you very much. Subscribe.